Hello, welcome back. Today we're going to be taking a look at cross products and their application with vectors. One important thing to notice is to get the cross product of two vectors, we're going to be using the determinant, something from linear algebra or from your matrices from algebra 2, of the vectors I, j, k. This does not work in 2 dimensions, but only in 3 dimensions. And we're going to take a look at some of the application in just a few minutes. But the first thing we want to do is we want to learn how to write the vectors, these two vectors, as a matrix. And it's not too hard to do. When you guys take linear algebra, you do this all a lot. You are going to do this a lot. Now, the important thing to remember, when you're talking about a matrix, you have these little hooks at the end here. And you're going to start off with I, j, k. That's your components, right? I is the 1 in the first one, j is the 2, k is the 4. Now, it does matter which one you write first, but I'm going to go do the first one. This 1, 2, 4, match them up with their like components. And then the negative 1, 3, 1. Like I said, it doesn't matter when we start doing the determinant how you order these. You'll get the opposite answer. We'll take a look at that in just a few moments. So now we want to take a look at how we calculate the determinant. Now this is my matrix. To get the determinant, we're going to use the cross product. Now you might recall we do have a product. The cross product is A cross B, something like this. So if I call this matrix A and this matrix B, vector A and vector B, their cross products will be A cross B. Now remember, there's a difference if we do B cross A. There are 2 ways we can do this. The first one is what we call expansion by minors. And to get the determinant, we tend to abbreviate it det of A. To get the determinant, what we're going to do is we're going to rewrite our matrix. But what you should notice is we no longer have the hooks. The hooks tells me it's a matrix. The determinant from algebra 2, remember, is going to give us a number. It's an application of our matrix. But to show that we have a determinant, we just use these little bars right here. And that's going to become 1, 2, 4, negative 1, 3, 1. And when we find the determinant here, the first thing we're going to do is we want to get the I component. So to get the I component, what we're going to do is we're just going to block off this row, this column, and this row. And what you notice is we're going to be left with this other smaller matrix, 2, 4, 3, 1 right there. And we're going to, and that's what we call, by the way, a minor. It's a minor part of our bigger matrix. So what we're going to do is we're going to find the determinant of this by multiplying downwards, like 2 times 1, and then subtract, multiplying going up, 3 times 4. Next, we're going to do the j component. Now, to do the j component, we actually have to switch signs. See, here it's positive. Here we're going to alternate, so it goes j. And we do the same thing. I am going to cover up this column and this row. And I do the same thing. 1 times 1. So we get 1 times 1 minus, because we're now going up, and it's going to be negative 1 times 4. So it's negative 4 right there. And then I got to do the same thing with the k component, plus k. And the last one, ready? Very simple. Cover up that row and that column, and I'm going to take the 1 times the 3 minus, going up, that becomes negative 2. And I can simplify this. This becomes 2 minus 12, or negative 10i. The j's, I get 1 plus 4, so I go minus 5j. And over here we get 3 plus 2, so plus 5k. And this is our determinant. Now, if you notice, the determinant here is in itself is a vector. We're going to talk about that in just a few moments. The importance of that vector today is going to help us do quite a bit. Now, another way we can find the determinant is, and this is probably what you're more familiar with from algebra 2, we can rewrite the first 2 columns. So if I do the same thing, I, j, k, 1, 2, 4, negative 1, 3, 1. I just rewrite the first 2 columns. And I'm going to go ahead and use blue for that. Like it'd be I, j, 1, 2, negative 1, 3. Now, not that you can see that, but that's actually in blue. Though now when you do the cross, now you're going to find the determinant a little bit longer. It takes a little bit longer to do. You're going to multiply going down I times 2 times 1, and that's going to give me 2i. And I just keep going down again. This becomes minus 4j. Anytime you go down, 4j. Anytime you go down, you add. It's going to be positive. So this would be times plus 3k, so it becomes plus 3k. And now we do the same thing, but we go up. Going up like a disco duck. But going up, you're going to subtract. So this becomes minus a negative 2k. I'm multiplying here. Going up again, this becomes 3 times 4 minus 12i. Be careful of the letter. And then going up again we're going to subtract. That becomes minus 1j. And I combine my like terms. There's my I, so 2 minus 12. Again, I get this negative 10i. Those are done. Looking at the j's, I get negative 4 minus 1, so minus 5j. And then I get this 3 plus 2, so plus 5k. And we do get the same. Both ways will get us the answer. The expansion by minors will be better for us in the long run because it's going to, we're going to be able to do that in our head a lot quicker. So, like we already said, the determinant of a matrix, as we noticed, is in itself a vector. And we're going to talk about a lot of applications for that. Matter of fact, we're going to kind of start now. Now, some of you guys have taken physics. Sorry, focus, right? Some of you guys have taken physics, and I know I'm much better with the... Hold on, it'll get there. Oh, we were like almost there actually. Come on, let me try it one more time. There we go. Sorry about that. Technical issues, huh? All right. In physics, you learned about the cross product of two vectors, and the cross product represents a vector orthogonal to two vectors. In other words, if the two original vectors form a plane, think of two lines intersecting in geometry. From geometry, any two lines intersecting form a plane. The cross product will be orthogonal to that plane, and that's what we learned and that's all this says down here from physics. That's your right-hand rule, right? If I want to take A cross B, if I want to find A cross B, I'm starting at A and I'm heading towards B. So it's going to look like this, right? And it's going up. But remember, the direction matters. We talked about that up here, right? A cross B, but what if I did B cross A? Well, with B cross A, well, I'm starting with B and I'm curling towards A, and the vector goes in the opposite direction. And that's what this says right here. So this goes in the opposite direction of A cross B. And that's going to become important for us when we get dealing with like slope. Now, note, the dot product A dot B, that's going to give us a scalar. We already learned about that. The cross product A cross B, this is always going to give us a vector. Alright, so I'm going to go ahead and take a pause right here, but you're going to go ahead and go to video 2, and we're going to start taking a look at applications. Okay, I'll see you then.